Hello and welcome everybody to my talk, which is entitled Characteristic and Necessary Minutiae in Fingerprints. And let me briefly note that this talk is based on joint work with Stefan Huckemann and Dominik Schumacher from University of Göttingen and Ivo Kern from the University College in London. To start with, let us consider a motivating example. So what you can see here are two fingerprints from identical twins, and indeed, so at least from a geometrical point of view, one would say that these two fingerprints do really look similar. However, using the point pattern, these red point patterns here in these images, one can distinguish between the two fingerprints with very high accuracy. And the question which arose to us was whether one can use the geometry for fingerprint to find out which of these red points actually do make the difference, which allows us to distinguish between the two fingerprints. So, to ensure that we're all on the same page, let me introduce some fingerprint terminology. So the point patterns here on the left panel in A, you already know these are called minutiae points. And what you're doing is you're considering this line pattern, this so-called ridge line pattern. These are the black lines in the image. And whenever these black lines either end or fork, you mark this point with a red dot. These points form the minutiae pattern. Moreover, the ridge line pattern introduces an orientation field via that you, in each point, you assign the orientation of the ridge line which is closest to that point. That forms this purple line pattern. In some points called singularities of the orientation field, we cannot assign a meaningful orientation in that manner. These are marked here with this green triangle. This is called the delta. So you have this delta type shape. Or when you have this 180-degree turn of the ridge lines, this is marked here with this red diamond. Furthermore, a fingerprint features a ridge frequency, and the ridge frequency indicates how dense the ridge lines are in a certain region of the fingerprint. So whenever the ridge lines are quite close to each other, the ridge frequency is very high, and on the other hand, when we have a low ridge frequency, that means the ridge lines are farther apart from each other. In practice, we can observe minutiae basically in two scenarios. On the one hand side, assuming a rather constant ridge frequency, but diverging orientation fields, this can be seen here on this top left panel. We have minutiae due to orientation field divergence. The second scenario can be seen on this top right panel, assuming a rather constant orientation field, and the ridges are running in parallel. When the ridges widen, giving space to new ridge lines, these are originating in new minutiae. Here we have minutiae due to what we call ridge frequency divergence. And in practice, we can, of course, also observe combinations of these two. So via summing orientation field and ridge frequency divergence, we end up with what we call the minutiae intensity. And this is our prediction for the occurrence of minutiae within a certain region. And indeed, what you can see is that there is quite a nice correlation between the points where minutiae do occur and the locations where we have high minutiae intensity. And the question which then arose to us was whether the minutiae intensity is also a good predictor in a quantitative sense. So it's the number of minutiae which are predicted by this, what we call mu here, also coincides this with the actual number of minutiae we observe in a certain region. So to analyze this, we said, okay, this is only meaningful when we have a look on larger regions. So we divided the fingerprint into several patches. This is indicated with this grid here. And then we accumulated, so we integrated the minutiae intensity over this grid, and then we compared that with the actual number of minutiae. So the statistical analysis led to this following graphic. So what you can see here on this horizontal axis is the integrated minutiae intensity. So this is a predicted number of minutiae which we expect in a certain patch called A here. And on the y-axis you can see the actual number of minutiae in that patch. And Poisson regression reveals that we have actually quite perfect correlation between these two quantities. So the slope of this regression line is close to 1. However, we observe in practice that there are more minutiae in the patches than there are actually predicted by our formula, which is visible by this small slope of the regression line. This leads to two terms. So we have on the one hand side, we have the minutiae which are due to the orientation field and rich frequency divergence. These we call the necessary minutiae. And on the other hand, we have the ones which are which exist beyond this, and these we call the random minutiae. And this, of course, gives rise now to the question: how can we distinguish between these two, right? So we propose here a mixture model. We assume that a minutiae pattern called zeta is actually a sample from a superposition of 2 point processes. So we have here a random setting, and these 2 point processes we call eta and psi, where eta models the necessary minutiae, and this contains fingerprint information by the minutiae intensity from the previous slide. And on the other hand, we have the random minutiae, which we do not equip with any further information because we don't have any. And last but not least, we have the latent variable W, so which indicates whether a certain minutiae is either necessary or random. To be more precise, from a statistical analysis followed that it is reasonable to model the necessary minutiae with a Strauss-Hartke process. So here we have this triangular activation function which is proportional to the minutiae intensity to include the minutiae intensity information. Then we have an hardcore, which in practice is due to the inter-ridge distance, so the distance between ridges, because minutiae can only occur on ridges, so they cannot be arbitrarily close to each other. And then we have another regularization term I cannot go into detail today due to time constraints. The random minutiae are modeled as a Poisson process with a certain intensity, which we do not know yet, but somehow correlates with the slope of this regression line, which we saw before. And now was the question, okay, how can we do inference on all these model parameters and on the latent variable W? So to this end, we propose a Markov chain Monte Carlo algorithm with alternating parameter update and label update steps. And implementing such an algorithm is unfortunately not straightforward due to intractabilities in the Strauss process and requires the application of the auxiliary variable methods. The resulting algorithm, which we call minutiae separating algorithm, or short MySeal, allows for Bayesian inference in both the model parameters and the label vectors. It is well mixing, as can be seen here on these from these trace plots on the bottom. On the right hand side, you can see the posterior distribution, marginal posterior distribution of the labels, where black means that it is likely for a minutiae to be random, and white means that it is likely that the minutiae is necessary. The knowledge about random minutiae now bears the potential for certain characteristicness, in the sense that we can distinguish better between the fingerprints from the twins from the beginning of this talk. For future work, we aim on including this knowledge also for improving matching rates of matching algorithms. So here are my references, and thank you for watching this talk.